I'm going to just give you a broad overview of how we've been using we've been using GeoClaw simulations to train machine learning models. And as everybody in the audience is probably aware, while GeoClaw is very efficient, these simulations are compute intensive. So, for example, if you wanted to predict what the tsunami will be at a certain point immediately after an earthquake, with sparse data, that is hard to do immediately. So we would like to develop some machine learning models to do that as a surrogate rather than running the full simulation. I'll just talk about four broad efforts. So first one is to try to develop a tsunami early warning using just gauge data in Cascadia subduction zone, just assuming that there are hypothetical gauges that does not exist yet. And a second project we had was trying to predict to try to do a real-time prediction. So rather than waiting for the tsunami gauge measurements to come in, we decided to try using geodetic measurements, which come in much faster, within minutes. And then the third project, which we are currently working on, is to do a real-time prediction of the inundation maps. Turns out training that model is much harder. And then the fourth project is actually a fundamental problem with the machine learning models that I'll discuss towards the end of the talk. This is a joint work with Chris and Bobby and Randy and Kenjiro. And of course, there were previous collaborators of Randy's who've contributed many things along with data sets and code and lots of different efforts. So thanks to Xinsheng, Diego, and Reika, and many others. So the idea is to consider the Cascadia subduction zone. We have this slab 1.0 geometry. We triangulate it so we can impose new slip distributions on it. We can come up with a kinematic rupture and generate seafloor deformations. So for example, these are four different random earthquakes we generated using Carhoon and Loewe expansion. And I believe we've sort of truncated some distance off of the epicenter. So, for example, these are four different realizations, which are slip distributions across these triangular fault geometries. And we use the triangular version of the Okada model, which was implemented in GeoClaw, and this gives us the surface seafloor deformation, which we use as an initial condition to the shallow water equations implemented in GeoClaw. So we were interested in, for example, if you look at this small little box, there's a strait of Honda Fuka, which sort of channels all the tsunami waves that occur in the deeper ocean before it arrives to the interior regions nearer to Seattle in Puget Sound. So the first machine learning task that we tried to do was, okay, suppose there is a hypothetical gauge that does not exist. But if there was a gauge out here at the entrance of the strait, and we had some early measurements of the incoming tsunami, can we train a machine learning model to predict what the tsunami waveform will be at these two locations, which are much closer to shore? So since the depth here is pretty deep, the tsunami water here tsunami surface elevation is not going to be very high. Whereas by the time it arrives at 901 gauge, which is near Discovery Bay, you'll see lots of nonlinear phenomena that happen. So it's not an easy prediction task. So for example, there's an example of a randomly generated synthetic tsunami waveform that comes in. So as soon as it starts coming in to the strait at 7:02, we look at maybe 30 minutes or 60 minutes of the incoming measurement, and we try to predict what's in the forecast window for the other two gauges, 901 and 911. So it's just a simple input to output supervised machine learning task. So we generated for the data for this task, we generated. Let me first show you what the tsunami waveform looks like. Although the tsunami has lots of variability outside in the open ocean for this event, by the time it channels into the Strait of Juan de Fuca, is mostly a planar wave. So this is a nice nice geographical region to test the machine learning models with a smaller data set. So it's a simpler task, relatively speaking. This is what the tsunami wave looks like near Discovery Bay. So we randomly generated 1,300 earthquake realizations. And then from those, we ruled out the scenarios where there were negligible tsunamis in the Strait of Juan de Fuca, which left us with slightly fewer realizations of around 1,000, less than 1,000 realizations. We split into training and test set. And we trained an ensemble of 25 neural networks. These were convolutional neural networks trained to take 30 minutes of the observation window data and then predict 5 hours of tsunami at the other two gauges. And we trained an ensemble. So we had 25 models that give you 25 different predictions. So for example, there's 25 curves here, and they somewhat disagree because the convolutional neural networks were randomly initialized, and there's randomness during the training. So you get 25 different and predictions, and we used the disagreements between these models as a measure of uncertainty in the forecast. Let me go to the next slide. So with the 30-minute window, you get a prediction that looks like this. So we use the standard deviation of the 25 different ensembles to draw an uncertainty band around our mean prediction. And you can see that it does a pretty good prediction for the first wave, but the later waves are harder to predict. But with the 60-minute window with more input data, it actually does a very good job of predicting what the full tsunami waveform will be over 5 to 6 hours. And if we just look at the maximum amplitude of the surface elevation and compare the predicted versus the observed, it's close. The closer to the 45-degree line, the better you do. And you see that for 30-minute window, there is some error, but with the 60-minute window, it lines up very well. So these convolutional neural networks are very good at predicting the full tsunami waveform. So this was our first study using machine learning models with GeoClaw. However, if you look at the timeline of the 2011 Tohoku event, the earthquake event happened around 2:46 p.m., but about 30 minutes later, you already started seeing lots of tsunami waves coming in. So if it's a near-shore event, unless you're in a very special scenario like the Strait of Juan de Fuca, which channels the wave and it takes a while for the tsunami wave to come in, having 30 minutes of measurements of the wave, the tsunami wave itself appears you have to wait too long to make a prediction. So we thought, okay, maybe there is a different way to get the measurements of the incoming wave. And our thought was, okay, maybe we can just use the seismic waves, which propagate much faster. So for the 1,300 earthquake realization we generated for the previous study, we also generated the seismic waves using the MudPy code, which uses Green functions for multi-layered half-space model. And so, for example, there's GNSS stations scattered across the West Coast, which are already in place. Unlike this hypothetical gauge that we mentioned for the previous study, they're already operational. And so we generate these synthetic events. So for one event, you would get these vertical and east-north direction displacements for that seismic wave. And so we took these measurements and we said, okay, maybe we'll pick 60 stations where we generate this data, and then we sub-selected some stations to see how well we can do with fewer amount of stations available. For example, 20 stations well-distributed, 40 stations well-distributed, and we try to group them into nearshore and inland groups of stations. And turns out we trained our convolutional neural network to take as input this geodetic measurements, which is available within minutes, and try to do the same prediction at Discovery Bay. And turns out that just with the geodetic measurements, we could do just about the same. We get the same amount of accuracy as when we use the 60 minutes of tsunami wave measurements itself. So on the left column, the curves are on top of each other because all the predictions are quite good. This is for one event, and this is another. And the difference is that this red prediction, which was using the geodetic measurements, you could potentially do much earlier on after the earthquake. And on the right, this is a Taylor diagram, and well, closer to the red point, you do better. And as you see, as you increase the number of stations that we used, you do a better job of prediction, which is what you sort of expect. And to quickly go over this diagram, we realized that if you use 20 well-distributed GNSS station measurements, you could do a very good prediction. It's sort of the summary. Okay. And next, we're now trying to predict the inundation patterns, not just the 1D tsunami time series. And turns out that's a much more difficult task. So we moved geometry to the Nankai Fault, which has this fault geometry. Oh, I must say that this depth axis is inverted. It actually should be curving downwards, but then these two perspectives will not match, so it's inverted. And then we calculated the FGMax or inundation pattern results by running GeoClaw simulations for randomly generated scenarios. And this is a region that's near a city called Kochi, that's very near shore. And these are, you see that there's a lot more variability in this inundation pattern compared to the tsunami waves you see in the Strait of Juan de Fuca. And these are the GNSS stations that was selected by Randy and Professor Reika Nomura at Tohoku University. And so these are the kinematic seafloor deformations, and these are the GNSS measurements at one of the station locations. And in this case, we kept increasing the data set size to see if we can train a model to do the prediction accurately for this inundation patterns. And turns out you need about 70,000. So finally, we're getting good training results after going back and training running more and more GeoClaw simulations. And about at 70,000, I think we're getting good results. So that's coming. And then, okay, so that's the sort of the happy news. I'll tell you the bad news. So these neural network, these deep learning models have a problem, and it's a stability problem. And this project is with Sana and Sangyeon and Kukjin and Randy. And I know you might have seen this somewhere else before, but neural networks are famously fooled by subtle, weird noise called adversarial examples. So if you train a neural network to classify the images on the left column, even if it did a good job for the original image, if you add minuscule data to this school bus, for example, and you get this right image, this is the blown up image of this perturbation, so it's barely visible, it's tiny. It actually classifies all the images on the right columns incorrectly as ostriches rather than the school bus or a pyramid or a dog. So mathematically speaking, this just means that the neural networks are very sensitive to certain perturbations to the inputs. And the bad news is that our tsunami prediction model suffers from the same thing. So we used what's called the projection gradient descent algorithm to find these examples. And these are measurements at two vertical components of the geodetic measurements at certain stations. And you see that if you perturb it an invisibly small amount, so you see that the dash and the blue are almost the same, but they are perturbed. The right side is showing the perturbations, and they're very, very small. So 0.2, less than 0.2 meters in amplitude. So that's about a 0.5% perturbation. And your tsunami prediction actually changes quite a lot by about 4 to 5 meters at the maximum amplitude. So 0.5 change perturbation in the input changes 36% in the output. So our prediction models suffer from the same kind of pathological behavior. And in this study, we found some low-rank space that if you filter out this perturbation in that direction, somehow this effect vanishes. So we were trying to perform some mathematical analysis to understand why this is happening. But of course, the catch-22 is that to calculate this low rank space, we do need to know the true input. So we understand the phenomena a little better, but it's not practically usable to stabilize and fix this problem. Okay, so future projects, we're of course continuing to do real-time inundation prediction results from GNS measurements at the Nagahama region. And of course, there's a big question of do these models perform well for data that wasn't synthetically generated by the same mechanism? So if you, for example, your seismic measure model is actually 3D rather than layered Earth, does it still do a good job? Does it do well for real data, things like that? And we could use these ML models as surrogates for source inversion or PTHA. So we're working on that. Of course, the big question is to devise a stabilization strategy against these adversarial examples, because if there is some subtle weird noise in that wrong direction, you could get a wildly wrong prediction, which is deeply worrying. These are the references, and one other machine learning project that I've recently started working on is trying to compress solutions coming out of ClawPack solves, which are on this AMR grid and is a very, it could be very large. If you stored your solution at every time step, for example, it's a very, very large amount of data. So we're making an attempt to compress the AMR solution using what's called implicit neural representations. So these are the references, and that's about all I have. And I'd be happy to answer any questions.